go. Well, welcome to the Headwaters Science Center 3:30 live show. I am going to pull down my mask so that I can project into the projectile laboratory here. And what we're talking about here is a subject that's coming up. Maybe ballistics interest you, maybe gravity interests you, but physics is my first love. So when we have forces, we all know this force. That force is gravity. That gravity force is the force of attraction between objects. The greater the object, the more that object attracts it, and therefore the greater the acceleration of gravity. So a lot of physics seems to come in through the sides and the back doors. In other words, it's not straightforward, observable, and understandable, perhaps even by some. But what we're going to do ultimately here is we're going to determine speed by using the acceleration of gravity, which we know to be about 32 feet per second squared. We're going to actually use the metric system because it works out for our calculations a little bit better. So that's about 9.8 meters per second. Objects are accelerating towards the Earth. And what does that mean? That means in the first second it's going 9.8 meters per second. But in the second it's going 9.8 plus 9.8 meters per second. Third second, this speed is going to increase. So we know that the farther you fall, the faster you go. This is problematic if you don't have a parachute. But if you're a rock tumbling off of a hill, why, that can be just okay. All right, so let's just look at something here. And let's start by challenging our mind to understand a notion. I'm going to have this little gadgetry device here that has a clever way of showing how gravity pulls on things. And what it does is there's a spring release, and it'll drop this one ball. I'll go two in because I think we're better. It's going to drop this one steel ball straight down, while the other ball is going to shoot out parabolically and then fall down. So the question I like to ask, audience, members who are listening, anyone who wants to find out truths about the universe, which ball will strike the Earth versus it's not the perfect ball to set in there. When I release the trigger, which of these balls will hit the floor first? Will it be the one that goes straight down or the one that flies out and goes down? We don't know till we try it, perhaps. Or maybe you already do know, but hold that secret because they will go down. We know that much. So this one has a further path out and down, and this one goes straight down. Now, we want you to use your ears on this one because your eyes may not tell you the exact truth. Our ears can actually hear faster than our eyes can see. And you're like, hey, my light goes so much faster than sound. Yes, but your processing of sound is so much faster than light that our ears are actually the better judge here. When you see umpires at baseball games, they listen for catches and base stomps and stuff. So I'm going to release this and let these two balls go down. Have you made your prediction? Lee, you made a prediction?
I have my prediction.
Okay, hold your prediction and we shall listen. So quiet, everybody. Quiet in the Science Center. Silent in here today. One's getting away. I'm running after him. I just caught it. So the acceleration of me equals the acceleration of that on two. So did you hear it? I did. I heard, in other words, the same. Even though this one had to travel further, where did the other one go, Lee? Oh, we can check the film if it had to. All right, let's amp up the game because really it works as well as we can show it on high speed, perhaps. So let's go all the way to see what we're going to go. Now, I'm not even going to chase it this time because it's probably going down the steps, and I'm probably not going to catch it. So again, with our ears, we're going to listen. Now, I pulled the lever further back, so the spring shot should be further, and it'll have to go even further to hit the floor first. Now, I should actually adjust that by making that knock off right about there. And the reason I'm adjusting it is because this piston will push that off at the same point that the device will drop that down. So let's listen again. Quiet, everybody. I promise not to chase that one. Listen. That's the sound of it going down the steps. And still going down the steps. Okay. One more. Oh, that was it. Okay, so we've shown something. Now, what does this tell us? And why are we calling this a ballistics lab? Well, what this tells us is that if we were shooting a gun with a bullet coming out the end of our barrel, that bullet begins, there we found our ball. That bullet begins to fall right when it leaves the edge of the barrel. But you say, oh no, it hits the target. Well, that's because the bullet goes fast. And so while it is falling, it takes a while. It gets way out there before it falls, and that's what we do in the fall when we sight our rifles. We essentially sight our rifles for the distance we feel that we're going to have to travel our bullet towards its target, and so that we can aim at it rather than make that adjustment there. And sometimes a good hunter will know this. It's a long shot, I have to make more of an adjustment. All right, well, we promised Hot Wheels labs, and we've shown something there with that. And let's move on with our Hot Wheels projectile laboratory. Put that over there too. Okay, so what we're going to do is we've got a similar launching device. And what it's going to do is it's going to shoot cars out here into the field parabolically like the other ball did and fall onto this. Now, we know the acceleration of gravity, and we also know this height to the drop here. And with those two pieces of information, given the distance here, the acceleration of gravity, and the height of this, we can actually figure out the speed of the car as it just leaves the track. Now, a lot of you are going, yeah, but what about air resistance? And I'm going to say, yeah, but it's not a lot. It's something, but it's not a lot, especially in an aerodynamically cool Hot Wheels cars that I have a collection, very many of. Now, if you are collecting Hot Wheels cars, as I once did when I was about 8 or 9, and began to do again when I was about 49, you'll know that the red cars are the fast ones. Not because they look the coolest. Hot Wheels does something to the red cars, so if you're betting on cars, bet on the red cars. All right, but when I'm doing physics experiment with Hot Wheels cars, there's one more thing I want to note. That is, these cars are the fastest they're ever going to be when you get them out of the box, the first day. After that, they start slowing down because there's no motors and systems, and they start getting beat up, and they start to fall, start to get knocked around, their wheels drag. So the first day that we put them out onto the field is their best day. So because we're using a physics experiment, we're going to move in with the standard set, the Hot Wheels Batmobile cars. Now, as you know with superheroes, Batman doesn't really have any superpowers, but I'll tell you this, Batman knows a lot about physics. He uses the power of physics. So we'll take some of these cars and we're going to measure that out and see if we can't predict the speed of these cars as they leave this, this launching device. So I'm going to put it on the first setting, and I've calibrated this a little bit. So I know this distance here. Let me get this set again. I've moved my table a some, and I calibrated this to 70. And I've used a styrofoam pad. Two reasons. I like the styrofoam pad because, as I said, where's my, those cars, when they hit, they don't get better, they get worse. And so these cars are going to get a softer deceleration. As you well know, it's not the fall that gets you, it's the instantaneous deceleration that kicks your can. So let's bring these cars out into the field, and then it's also going to, in this styrofoam material, leave a mark. Those of you teachers that are planning on doing this next week in school, I prefer the styrofoam, and of course you know where to get your Hot Wheels because you've been collecting them too. So let's let the first one go, and let me make sure all my measurements are correct. I'm 70 out because I've already pre-tested and pilot testing and know they go at least 70. So let me set it free. So here's the first mark. So here's one. I'm going to circle that. That's one of my marks. Well, let's, before we do the very exciting mathematical calculations, let us simulate 2 or 3 different projectile sets. There's number 1. And number 2, are we still in camera here? We'll set it out. Now, I've tightened up the tension, so our prediction is naturally that it should go further and thus faster, okay? Further equals faster because, as we said before, gravity is a constant. It'll pull it down at the same rate regardless of the speed. And that surprises people sometimes, but actually it's a pretty interesting notion and something to understand. So let's send that one out there. Our mark for that one I see. Oh, we got a nice mark for that one. That one landed on 4 wheels. We're gonna take the center of that one because of that. So there was the first, second. Let's take our final mark here. We'll go all the way to what this thing will do for us. Same car. And the reason one of the things I do with the closed set is that when I'm comparing cars to cars, it's the best way to do it. But we're using the same car, and so we don't believe that the dynamics of the car have changed much during these 3 tests. So again, we've tensioned the spring to the most it can go, and so we're expecting it to go the furthest. And sure enough, it did. It went out to here. So this car here went to there. All right, now if we add our numbers, the first one is 70 plus, well, I better go this way, 12, it looked like from there, plus 12. So that one's an 82. That one went out 82, and the first one, I've got my very interesting calculations over here, 82 centimeters. And I'm doing the mathematics for you today because whether you believe it or not, I actually love the mathematics a lot, because when you get things like velocities and you get your centimeters to work out and all the factors fall away and you get a number that you understand and are comfortable with, like miles per hour, it can be really really rewarding. So the first one is 70, the second one is 70 plus, well, let's go 54 and a half. So that's going to be 124 and a half centimeters. 124.5 cms. You can see this is my workstation over here. And the third one, the one that went the furthest, which it wasn't even, it wasn't equal. And while we didn't do the in-between one, the tension of this didn't keep, it wasn't linear. Let's just put it at that. The second one is out 70 plus, let's call that 65. So that's 135 centimeters out. 135. So let's do our figures, and I have done some of the pre-calculations. If you want the full formula, I have that here. Maybe give them a full look at the sheet. Is that in sheet in size? Capture that for about 2 or 3 seconds. You'll see the formula I'm using is right there. Speed equals distance times the square root of gravity, which we know, divided by 2 times the height. All right, so let's done that. I've done some of the pre-work on that, as I said, and I've got my converting factor here, which is going to give me speed in centimeters per second by multiplying out simple figures like 2.43, which is where that worked out for our height, 423 times 82 equals 198 centimeters per second. And you go, I really don't know what that is. Well, let's keep going. The next one is, let's just do the first one and the last one because they are the most telling. Yeah, 135, oops, I made a mistake. 135 times, my number of my converting factor is 2.423 equals 327 centimeters, here, 27 per second. You can see it's almost, that's about 50% faster on that. Let's just do the middle one just for grins. 124.5 times 2.423 equals 301 centimeters per second. Now you're dying to know what that is in the English system, the one that you're used to driving your cars around by. So I did bring that converting factor here as well, and times 0.02237 equals, for this one, 6.7 miles per hour. You thought, I'm a little disappointed. I thought they went faster. Well, the truth is the truth, and you can love it or leave it, but I prefer to love it because it reveals the secrets of the universe when you listen to it. Times, and I know it's just riveting watching a guy do the mathematics for you, so I'll do it quickly. 3.7, I've done a little bit of rounding, and this equals 7.3 miles per hour. It's down there, I expect that. That's what I see regularly and often. Oh, you say, yes, you know. Now you know your Hot Wheels cars are moving along, but I wanted to bring another thought experiment into this. And it goes something like this. Could we do this on the moon? And the answer is, yeah, we could. But we could still calculate the speed, because that should be the same. We bring in our table width, we're bringing our cushion foam board width, and the only thing that's really going to be different on the moon is the acceleration of gravity. which is going to be less, about a sixth. So what's actually going to happen in the car here, since the acceleration of gravity is 1/6, they're going to go out 6 times further. They're going to go through the wall, into the alley, way out there before they hit the floor. They're going to go further because it's going down slower. Well, what about a place like Venus, which is a planet that's just a little bit smaller than Earth? About 10%, 11%, somewhere in that range. Well, yeah, we can do the same experiment there, but again, they're going to go about 10% further. And if they go 10% further, they're going to go a little bit faster. So they're going to be going, the speeds will be the same, but they'll go a little bit further is what I meant to say. The speeds are going to be the same because we've got the same accelerator. So they're going to go about 10% further there. Now, all right, so we're ambitious. We've got a big space budget. What if we bring this thing up to Jupiter? Now, Jupiter is a huge planet. And sometimes it's surprising to people that Jupiter's acceleration of gravity, if you can stand on the surface at all, is only about 2.5 times more because it's a gas giant. It's actually a failed star. We live in a binary star system, but not everybody agrees with that. I just love it that way. And what's going to happen is that this thing is going to go and fall down about here. It's going to fall down right quickly. Well, let's say we had our heat-resistant materials on, our asbestos suits, or we brought it to the sun. Well, the gravity on the sun is about 28 times Earth. So what's going to happen is it's going to go, and it's going to go down really fast. And I make that sound because I don't know. I'm too hot. I gotta go. It's getting too hot up here. That's the end of the show. Welcome to Hot Wheels Projectile. Come visit us at the Science Center, Monday through Saturday, 9:30 to 5, Sundays 1 to 5. We'll play around with cars, physics, animals.